Forging Vision Foundation Models for Autonomous Driving. This is a discussion of a paper. It's within the series of foundation models for embodied decision-making agents. So we are discussing papers, like I said in the introduction, in the announcement, that I'm going to discuss research papers, industry applications, seminars. So anything actually relevant that I think is important for foundation models, for embodied decision-making agents, in other words, for robots. I hope this series is useful because the field is going so fast that it's incredibly important to find the right cadence and also to not lose sight, not lose the forest from the trees kind of thing. So this series is an endeavor to structure the thinking, to take advantage of all the incredible advancements, and also to be ready for any big changes. Like I said in the prelude again, or in the announcement, we believe this is a massive paradigm shift. So this is not just another innovation or something. We have a massive paradigm shift going from what used to be machine learning, which is, let's say, we have a compression of data and then some applications, dedicated models applying that particular data to a specific problem, towards a very generally trained foundation model, a multimodal foundation model that takes into account all kinds of sensor information. And then that foundation model is the base for fine-tuned decision making, in other words, for, let's say, a self-driving car. So this paper is an attempt to structure the thinking in the self-driving space. And vision foundation models for autonomous driving are models that are, the attempt of these models is to, or the end goal is end-to-end learning to drive. This is the end goal, something Tesla has discussed several times already. They've even showed us a demo a couple of months ago. They're in the works at CVPR about 6 months ago. They said they're not ready yet to show the models or discuss them. We believe that this year's CVPR, they will. We'll see about that. But the idea, of course, is end-to-end driving. Now, what is end-to-end driving? In this paper, they discuss several papers that try to attempt that. Now, you have to be, of course, very careful when we discuss these things. But the problem of end-to-end autonomous driving is to find a way to represent the current traffic scenario, predict future layouts, make decisions based on those layouts, and then link those decisions to lower-level actuators. So this is the fundamental idea. Now, let's go through the paper, and then I will sort of try to point out what's really important. I think first, they start by describing the two key problems in autonomous driving: data scarcity and task heterogeneity. I don't quite agree with that, in particular of the data scarcity. The data scarcity is, there is enough self-driving data. The problem, of course, is to capture the data and to capture the relevant data. Whether you're Tesla, AI, or whoever you are, there's millions and billions of miles driven every year in the United States by humans. So we have the potential to collect the data, and as opposed to, let's say, folding clothing or fixing a coffee machine or whatever else we're trying robots to do, or even sorting things in a factory or fixing stuff or whatever it is, the sensor capture of autonomous driving, in fact, is pretty standard, because you have a couple of places where you can put a monocular camera, or if you want more lenses, it's fine. But a couple of places, I mean, the space where you can put the camera is relatively limited, and then you have a couple of control mechanisms. The gas, the brake, and the steering wheel. Now, in that sense, the UI between the decision-making agent and the control, the low-level controls, that interaction is pretty straightforward. And in that sense, I would say data scarcity is not the problem. The problem is, how do we take advantage of this situation. And this is a similar problem like we had before machine learning, and then large language models came up. We already had the data in the, let's say, the data was available, let's say, even before the internet, the data was available. There were books and books and libraries of books available. Then, of course, it was hard to capture that in a sort of machine understandable way. The internet was the rollout for that, and it enabled that. And that's where we ended up with GPT and Llama and BERT and all these models. What they did is take advantage of a machine version of textual data, which has been collected over centuries. Now, the same is happening in the self-driving car space right now, and a little bit less, but also in the rest of the embodied decision-making agent space. And what the authors here are saying is that this is a problem. Now, I would say yes, but it's being solved. Task heterogeneity is, in my opinion, well, you could call it the problem. It just means that, well, we have different sensors, we have all kinds of different tasks, and most importantly, in the traffic scenario, we have a much, much more dynamic situation. So in a sense, and I will discuss this a little bit later, but if we talk about, let's say, representing an image, for example, we talk about the representation of a certain traffic scenario. That traffic scenario is changing all the time, and that is a relatively unique for autonomous driving, because let's say in a factory robot, the situation is not as dynamic. Things change, but not as dynamic in a kitchen, or if you have a robot that helps elderly people, or whatever your robot may be doing. I think traffic has a much more dynamic scenario. So the heterogeneity of tasks, I would say, yes, it's a problem, but in a sense, well, this is the problem, right? I mean, otherwise we wouldn't even be talking about it. But nevertheless, that's how the authors sort of structure this situation. Now, what they're doing then is sort of trying to, they're not very clear about what their sort of, what their opinion is about all this. But in my, the way I see it is, they're saying, look, fundamentally end-to-end learning, as it has been shown in AlphaGo Zero, should be at least massively supported by simulation. And that is an area where I think a lot more work can be done, because the authors are also talking about innovations, in particular the occupancy networks and Nerfs, bird's eye view, BEV, Nerfs, those sort of things. I think what they're trying to say here is that in the realm of perception, image classification, we've made a lot of progress, and we've solved, in particular, the problem of depth. Now, for Tesla followers, this is nothing new. Tesla has solved the depth problem already quite a while ago with stereo technology, meaning you can use two lenses and then generate depth from there. We have Nerfs now, and we have occupancy networks. I'm not quite familiar with the exact technology, so I don't want to dwell too much, but the authors are saying that those innovations allow for better representation. Now, what they're also saying, which is incredibly crucial, is that we can now use transformer architectures to represent the traffic scenario, which will lead towards the world model, which is really the conclusion of the paper. And I think the world model, it's a word that has been used by Tesla also several times. The world model is a representation of a traffic scenario and the ability to predict and steps into the future. This is what the world model is. The world model is also the base for model-based reinforcement learning. So I think I'm giving away really the gist of this paper, which is we have the ability to create a world model, again, a representation of the environment, of the traffic scenario. In the case of a robot, here's a quote: "The world model is a long-standing concept in artificial intelligence, which is usually defined as predicting future states conditioned on action and past observations." Okay, so I forgot the action thing. So we have a traffic scenario, and we have the predicted action given the next scenario, and then also the predicted development of the world model. This is really what end-to-end driving is trying to achieve. When Tesla's talking about the world model, this is what they're trying to achieve. Now, this paper, the good thing about this paper is they're going back to Schmidt-Huber in the 1990s that introduced this concept. They're showing papers that are trying to achieve this in a piecemeal way, that have theoretical aspects of it. I don't want to go into details here. Again, fundamentally, what the world model is trying to do is, again, represent I would say the world model in essence is a model-based actor, critic, reinforcement learning approach towards the problem of robotics. This is how I would characterize it. The model is the world model, and then you have an actor-critic algorithm, which means that you have an actor that has state and actions, and then you have the critic, which evaluates, which gives a value function for different tuples of state actions, and then that, and also iterates the world model based on. So the critic's value will change the action tuple, and then the action tuple will change the world model. You can see that this interaction, this recursiveness between all these different domains is really what's so difficult and exciting. And I think the eventual end-to-end driving solution in self-driving cars or robots in general is going to be the solution, or the solution to the problem of this interaction is really what, in my opinion, is going to drive any kind of self-driving car technology in the future. So again, we have the world model. Now, how can we get that world model? Again, we can go back to perception. First, we need some sort of three-dimensional representation that can capture depth, which Nerfs can do, occupancy networks. We need that dynamic representation, which occupancy networks can do, conditional occupancy networks. Tesla spoke about the CVPR 2023. I'm sure advances have been made. Some of the papers here, there's 250 papers listed in this paper alone. So there's some advances made. What I mean with dynamic occupancy networks is just, if you have a bus in front of you, you also want to model how this bus is moving. Now, this can be done fundamentally through a multimodal mask autoencoder. This is the key, I believe, and there's another paper that I'm going to discuss in the sort of context of Nerf, that's multimodal mask autoencoders into account. Over in that paper, it's sound and video, but we could generalize this for the embodied decision-making agent problem in the following. You have a multimodal transformer architecture. So you bring in sensor information from images, sound, maybe even haptic information from the tires in the case of a car, haptic information from the fingers in the case of a humanoid robot, and you can bring in other sensors if you humidity, all kinds of things, but let's say sound and video in particular, and then you use a mask autoencoder, whether it's the BERT model where you have sort of random masking and then predicting filling up of those masks, or whether it's next word prediction or next token prediction like GPT. That's those, you see, those are already problems that we could have another 20-minute discussion about with which one works better in which scenario. But fundamentally, let's just stay here that I think foundation models and transformer architectures are here to stay, and the multimodality of those are at least potentially the solution towards the world model. This is the statement I want to make here. I want to point out one paper that the authors focus on, which is a paper by the name of Planning-Oriented Autonomous Driving. So this paper, the attempt is to build an end-to-end pipeline, and that's really important because you kind of have to think of the architecture in terms of the pipeline and make sure that you have a workflow in the model that starts with an input and works its way through to the planning space. If you explicitly define the architecture in a way that you have an input and then a convolution,
of transformations of that input towards the end goal, which is a planning decision. So you have what Elon Musk would call, you have the input and then low level decisions such as acceleration, brakes, turn right, turn left. If that's the goal, then you have to think in terms of the architecture. So what these people do in this paper, they start with track. So they have several modules. One is called track, one is called map, one is called motion, one is called occupancy, and then planning. So and all of these have specific tasks to fulfill, but the important thing is they are convolved. So this is not a separate task, decision making process or anything like that. They convolve, and the authors talk about the efficacy, and they go one by one. Let's say in track, jointly performs detection and multi-object tracking. Then we have map, which is you create the map on the fly while you're driving. Motion is transformer structure for the motion task with highly abstract queries for dynamic agents, QA and static map, QM, from track former and map former respectively. Map former predicts all agents' multimodal future movements, i.e. top K possible trajectories. So what motion does is it looks at, okay, where am I? And what's the probability that I'm going to do something? And then also what's the probability that other people are going to do based on the idea that I'm going to do something. Occupancy puts all of this together, and it incorporates both scene level and agent level semantics into a combined dense model, which then is fed into the planner that converts raw navigation signals, turn left, right, and etc., into learnable embeddings. So in the end, okay, you want to have also an algorithm. Let's not forget something here has to be able to learn, something has to be able to be updated, weights and biases have to be formed and updated, and the learning happens in two stages. One is only the perception, and then the other is the end-to-end planning module is trained separately. I don't know exactly why the authors are training it separately, but I guess there's some benefit to do that. I think this idea of having an end-to-end learning algorithm, it incorporates all different modules that you would have in a separate type of algorithm as well. But the point is, in this case, what's important is that you're convolving it into one big model, and the um, the signal is being transformed within the model as one. So this is a one big optimization problem that is being solved versus several small optimization problems. I think this is really where I think the rubber meets the road here, pun intended, and then also other things can happen, such as human robot. I'm going to talk about this a little bit more in a different episode. I think as I'm starting this new series with foundation models for embodied decision making agents, I'm going to have to find my sort of tap my way through. The most interesting thing for me is really understand what are the problems, how are they being solved, and where is the technology actually happening, whether it's within Tesla or within other entities. So to summarize this particular paper, I think it's a great summary for what's happening in the autonomous driving space, in particular when it comes to foundation models. I think this is the future. To this to all the ideas and self-driving problem. Thank you.